My dear students, welcome back to our channel. In this video, I will be explaining the MCA second semester subject Operations Research as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 1 first important short question is: define operations research. Operations research or is a scientific approach to decision-making that uses mathematical models, statistics, and algorithms to solve complex problems. It helps organizations use their resources like money, time, and manpower effectively to achieve the best possible results. Key idea or focuses on optimization, finding the best solution out of many options. Example: imagine a factory making two types of products with limited raw material and labor. Using all techniques like linear programming, the factory can calculate how many units of each product to make, how to maximize profit or minimize cost. This avoids guesswork and ensures better decisions. Importance: helps in planning and scheduling. Useful in transport, manufacturing, business, and military. Saves time and cost while improving efficiency. Memory tip: think of OR as a mathematics-based manager that finds the best way to use resources for maximum benefit. Next important long question is: 2. What is a linear programming problem, LPP? Linear programming problem, LPP. A linear programming problem, LPP, is a type of mathematical method used in operations research to find the best solution, like maximum profit or minimum cost, from a set of choices. It uses linear equations or inequalities to show limitations like money, time, or resources. Key parts of LPP. 1. Decision variables, what to find, example, number of products. 2. Objective function, goal to maximize profit or minimize cost. 3. Constraints, rules or limits, example, raw material, labor. Example: a company makes chairs and tables. Profit, 200 rupee per chair, 300 rupee per table. Limited wood and labor are available. Using LPP, we can calculate how many chairs and tables to make to get maximum profit. Memory tip: think of LPP as math that helps choose the best plan under limits. Next important short question is: 3. State any two assumptions of linear programming. Two assumptions of linear programming. Linear programming, LP, is based on some assumptions to make solving problems easier and more accurate. Two main assumptions are: 1. Proportionality. The effect of decision variables is directly proportional. Example: if one chair takes 2 hours to make, then 2 chairs will take exactly 4 hours. This means there is no extra cost or time for producing more units, it increases in the same ratio. 2. Additivity. The total effect of all activities is the sum of individual effects. Example: if profit from one chair is 200 rupees and from one table is 300 rupees, the total profit for 2 chairs and 1 table is 2 times 200 plus 1 times 300 is equal to 700 rupees. There are no hidden benefits or losses when activities are combined. Memory tip: think of LPP assumptions as straight-line rules. Everything grows or reduces proportionally and adds up neatly. Next important short question is: 4. What is the objective function in LPP? Objective function in linear programming. The objective function in a linear programming problem, LPP, is a mathematical formula that represents the main goal of the problem. This goal is usually to maximize or minimize something, such as profit, revenue, or cost. It is written as a linear equation of decision variables. Example: if a company makes 200 rupee profit per chair, kiss smiley. 300 rupee profit per table, why? Then, the objective function to maximize profit is Z is equal to 200x plus 300y. Z is equal to 200x plus 300y. Here, Z is equal to total profit. X, Y is equal to number of chairs and tables. Easy trick. Think of the objective function as a target formula. It tells you exactly what you are aiming for, more profit or less cost. The LPE will then find the best values of X and Y that achieve this goal. Next important short question is 5. Define feasible solution and optimal solution. Feasible solution and optimal solution. Feasible solution. A feasible solution is any solution, set of values for decision variables, that satisfies all the constraints of a linear programming problem, LPE. Example: if constraints are x plus y less than or equal to 10, x greater than or equal to 0, y greater than or equal to 0. And we choose x is equal to 4, y is equal to 5, this is a feasible solution because it satisfies all conditions. Optimal solution. An optimal solution is the best feasible solution that gives the maximum or minimum value of the objective function. Example: if the objective is to maximize Z is equal to 200x plus 300y, the values of xx and yy that give the highest profit Z, while satisfying constraints, is the optimal solution. Quick tip: feasible is equal to possible. Optimal is equal to best among all possible. Think of feasible solutions as all valid choices, and the optimal one as the winning choice. Next, Unit 1. Top 5 long questions. First important long question is 1. Explain the steps involved in formulating a linear programming problem with an example. Steps to formulate a linear programming problem, LPP. Linear programming is a mathematical way to find the best solution, maximize profit or minimize cost, while following given rules, constraints. Let's see the steps. Step 1. Identify the decision variables. These are unknown values we need to find. Example: a factory makes chairs, kiss smiley, and tables, y. Here, x is equal to number of chairs, y is equal to number of tables. Step 2. Define the objective function. This is what we want to maximize or minimize: profit, cost, etc. Example: profit per chair is equal to 200 rupees, per table is equal to 300 rupees. Objective function. Z is equal to 200x plus 300y, maximize profit. Step 3. Write the constraints. These are the limits on resources, time, materials, etc. Example: wood limit 5x plus 10y less than or equal to 200, total wood less than or equal to 200 units. Labor limit 2x plus 3y less than or equal to 60, total hours less than or equal to 60. Non-negativity. X greater than or equal to 0, y greater than or equal to 0. Step 4. Formulate the model. Combine everything. Maximize Z is equal to 200x plus 300y. Subject to 5x plus 10y less than or equal to 200, 2x plus 3y less than or equal to 60, x, y greater than or equal to 0. Step 5. Solve the LPE. Use graphical method for 2 variables or simplex method for many variables to find the optimal values of x and y. Easy way to remember. 1. Decide variables. 2. Write objective. 3. Add rules, Constraints. 4. Solve to find the best solution. This structured approach helps businesses plan resources smartly and earn more profit. Next important long question is: 2. Solve a linear programming problem using the graphical method. Problem example. Maximize z is equal to 3x plus 2y. Subject to x plus y less than or equal to 4. X plus 2y less than or equal to 6. X greater than or equal to 0. Y greater than or equal to 0. We want the best, largest value of z while satisfying the constraints. Steps: graphical. 1. Draw axis, x on horizontal, y on vertical, only first quadrant since x, y greater than or equal to 0. 2. Plot each constraint as a straight line, replace less than or equal to by happy smiley. X plus y is equal to 4 intercepts when x is equal to 0, y is equal to 4, when y is equal to 0, x is equal to 4. X plus 2y is equal to 6 intercepts, x is equal to 0, y is equal to 3, y is equal to 0, x is equal to 6. 3. Shade feasible side of each line, the side satisfying less than or equal to. For both constraints, the region is below the lines. 4. Feasible region is equal to common shaded area that also lies in x greater than or equal to 0, y greater than or equal to 0. This will be a polygon, closed area. Find corner, extreme, points. Vertices of the feasible polygon occur where lines meet. Intersection of axis, 0, 0. Intersection of x plus 2y is equal to 6 with x is equal to 0, 0, 3. Intersection of the two constraint lines, solve. X plus y is equal to 4 and x plus 2y is equal to 6. Subtract y is equal to 2y is equal to 2, so x is equal to 2. Point 2, 2. Intersection of x plus y is equal to 4 with y is equal to 0, 4, 0. So corner points 0, 0, 0, 3, 2, 2, 4, 0. Evaluate objective at each corner. Z, 0, 0 is equal to 0. Z, 0, 3 is equal to 3. 0 plus 2, 3 is equal to 6. Z, 2, 2 is equal to 3. 2 plus 2, 2 is equal to 6 plus 4 is equal to 10. Z, 4, 0 is equal to 3. 4 plus 2, 0 is equal to 12. Conclusion: optimal. Maximum Z is equal to 12 at point x, y is equal to 4, 0. So produce x is equal to 4, y is equal to 0 gives the best result. Quick memory tip. Graphical method is equal to draw shade find corners plug in. Works best for two variables and is great for visual understanding. Next important long question is: 3. Discuss the Simplex method for solving LPP in detail. Simplex method for solving LPP. The Simplex method is a mathematical procedure used to solve linear programming problems, LPP, especially when there are more than two variables, making it difficult to solve graphically. It is a step-by-step tabular method to find the optimal, maximum or minimum solution while satisfying all given constraints. Key idea. It starts with a basic feasible solution, usually by introducing slack variables, and improves the solution step by step until no more improvement is possible. Steps to solve. 1. Write the problem in standard form. Convert all inequalities into equations by adding slack variables to represent unused resources. Ensure all variables are non-negative. 2. Set up the initial simplex table. Arrange all coefficients of variables, constraints, and the objective function in a table. 3. Identify the pivot column, entering variable. Choose the column with the most negative value in the objective row for maximization problems. 4. Identify the pivot row, leaving variable. Divide the RHS values by the positive pivot column values. The smallest ratio identifies the pivot row. 5. Perform pivot operations. Make the pivot element 1 and adjust other entries using row operations to maintain feasibility. 6. Repeat steps 3 to 5. Continue selecting pivot elements until there are no negative values in the objective row. 7. Read the optimal solution. The variables in the table show the final values, and the objective function gives the maximum or minimum result. Example. Maximize z is equal to 3x plus 2y. Subject to x plus y less than or equal to 4. X less than or equal to 2, y less than or equal to 3. X, y greater than or equal to 0. After applying the simplex steps, we get x is equal to 2, y is equal to 2, z is equal to 10. Why simplex is easy to remember? Think of simplex as a game of tables. Pick the most negative column. Choose the smallest ratio row. Pivot, adjust, repeat. It's systematic, clear, and guarantees the best solution. Next important long question is 4. Explain duality in LPE with an example. Duality in LPP. In linear programming problems, LPP, every problem, called the primal, has another related problem called the dual. Solving either one gives us the solution to the other. This concept is called duality. Duality helps us check the correctness of solutions, understand relationships between resources and profits costs, solve large problems more easily. Basic rules for writing the dual. 1. If the primal is maximization, the dual will be minimization and vice versa. 2. The number of constraints in the primal is equal to number of variables in the dual. 3. The coefficients of the objective function in the primal become the RHS values in the dual. 4. The RHS values of the primal constraints become the coefficients of the objective function in the dual. 5. If the primal constraints are less than or equal to, the dual variables are greater than or equal to 0 and vice versa. Example. Primal problem. Maximize z is equal to 3x plus 5x. Subject to x plus 2x less than or equal to 8. 2x plus x less than or equal to 6. X greater than or equal to 0. Dual problem. Minimize w is equal to 8y plus 6y. Subject to y plus 2y greater than or equal to 3. 2y plus y greater than or equal to 5. Y greater than or equal to 0. Explanation of example. In the primal, we are maximizing profit using variables x and x. In the dual, we are minimizing the total cost of resources y and y. Solving either problem gives the same optimal value for z and w. Easy way to remember. Think of duality as a mirror image. Max left and right arrow min. Variables left and right arrow constraints. Profits left and right arrow costs. Duality is like looking at the same problem from two angles. The primal focuses on using resources effectively. The dual focuses on pricing resources efficiently. This makes duality very powerful in business and operations, as it ensures optimal resource allocation and correct decision-making. Next important long question is 5. What is sensitivity analysis in LPP? Explain its significance with an example. Sensitivity analysis in LPP. Sensitivity analysis, also called post-optimality analysis, in linear programming problems, LPP, is the study of how changes in the input data affect the optimal solution. In real-life problems, data like profits, costs, and resource availability may not be fixed. Sensitivity analysis helps decision-makers understand how much these values can change without affecting the optimal solution. Whether a solution remains valid if business conditions change. Key aspects studied. 1. Objective function coefficients. How changes in profit or cost per unit affect the optimal solution. 2. Right-hand side, RHS, of constraints. How increasing or decreasing available resources affects the solution. 3. Shadow prices. The worth of an additional unit of resource. Why it's important. Real-world decisions. Businesses often face uncertainty in costs and resources. Risk management helps managers prepare for what-if scenarios. Efficient resource use identifies which resources are most valuable to invest in. Flexibility allows businesses to adjust production plans quickly. Example. A company makes two products, P1 and P2. Maximize Z is equal to 40x plus 30x. Subject to 2x plus x less than or equal to 100 material. X plus x less than or equal to 80 labor. X greater than or equal to 0. The optimal solution might be x is equal to 30, x is equal to 50, z is equal to 2700 rupees. Now, if the availability of material increases from 100 to 110, sensitivity analysis helps us see if the current solution, x is equal to 30, x is equal to 50, is still optimal or if we need to recalculate. Similarly, if profit per unit of P1 changes from 40 rupee to 42 rupees, we can quickly analyze its impact. Easy way to remember. Think of sensitivity analysis as a what-if tool. What if resources change? What if costs or profits change? It tells us how sensitive the solution is to changes, making it practical for dynamic business environments.